So, hello and welcome back to Calculus 1 and with the start of chapter 5. Section 5.1, which is approximating area under the curve meaning a function, f of x. So, have you ever wondered what's the area under, let's say, a square root curve? Or x squared curve, or x cubed curve, right? Because you wonder a lot of things, right? Well, they should be on the list too, right? What's the area under this curve? Because you know basic areas. You know area of the rectangle, square, triangle, trapezoid maybe, parallelogram maybe, circle, right? All of those have formulas that are thousands of years old. But what happens if you do not have one of those special shapes, right? What if you have square root? What if you have x squared or something that is curved, right? So let's take a look at this. I'm going to draw, let's say, a square root function. And I'm going to wonder what's the area from 0 to 4. Now, this is interval, meaning x1 and x2. So, I'm going to make these rectangles at 1, 2, 3, and I'm just going to end at 4 because that's where the story ends. And I'm going to notice that, you know, they do look, well, the first one looks like a triangle, but these guys look somewhat like rectangles, right? You have three sides are okay, and then the fourth one is a problem. Well, this is approximation, so it's okay, right? Now, to make a rectangle, let's go, so this is the first, this is the second, this is the third, right, and the fourth. To make a rectangle, let's say in the second one, I have two options. Option 1, to use red, which is left hand approximation, or to use blue, right hand approximation. So I have left hand approximation and right hand approximation. So clearly they're going to give me different answers, right? Again, I'm approximating. So you may pick any. We are going to have better approximation in Calc 2, so you will never be actually using these. But these are important to bring us to the next level right now. Now, I have this situation between the red and the blue, everywhere, where you see that in this particular example, blue is going to overshoot the area and give you the approximation bigger than what the area actually is, right? Because the actual area is underneath the black line. And the blue rectangles, let me just point out a blue rectangle over here, right? That's a blue rectangle. We all see it, right? That's a blue rectangle number 1. Well, clearly, at least half of it is an error, right? then we have the next blue rectangle right here. That's a blue rectangle as well. How much is error? This much over here, right? That corner is all error. So another blue rectangle right there, and I have the error in here. So I have 4 blue rectangles, and when I add areas that I get from blue rectangles, the area that I get is going to be bigger than the area that it's actual area. Now the red ones in this case are going to undershoot the area. Do you see that the first rectangle is actually 0? There's not even area to the first rectangle because it just sits on the x-axis. So there's no height to it. So the first rectangle in red is 0, and then we have the other 3. So all of these are terribly wrong, right? But we can improve on them. And that's one of the great things here. Now, let's go and calculate red in this case. So left hand. So area 1, the first rectangle, is going to be is going to be 0, yes, but I want to calculate this. So I have my length times the height. Do we all agree that that's the area of the rectangle, right? Do we also all agree that the length is 1 because it's from 0 to 1? Times the height is 0. And we get 0 for the first one, right? A2, length times height. Length is again 1, and now height is f of 1. Do we see that? Do we all see that the height of the rectangle is f calculated at 1? Now we know what f is. F is square root. So now we have 1 times 1, which is 1. Third rectangle, A3, is 1 times f of 2. F of 2, right? So let me box off that rectangle. Do we see that the height of that rectangle is calculated at x equals 2 because that's the point that hits the black line, right? So 1 times square root of 2, which is about 1.4, so 1.4, good enough. Finally, A4 is 1 times f of 3, which is 1 times square root of 3, which is 1 times 1, about 7, which is 1.7. The actual area is approximated by A1 plus A2 plus A3 plus A4. I had 4 rectangles there, and that is going to be 4.1 when you add all of these values. Yes?
And that was using the left hand.
Yes, red one, left hand. Now we're going to repeat this with the blue. Guys, what gets to change in here? Your function gets to change. I put ln x, I put e to the x, I put x squared plus 3. That's the only thing that's changing. The rest of the calculations are the same. You're making the rectangles and you're going across. So A1 is going to be 1 on the length times square root of 1, which is 1. So 1 times square root of 1, so length times the height. Look at the height of your blue rectangle. Do we all agree that you are calculating the height at 1 to come up with the height of the rectangle? And the width of the rectangle is 1 unit. So A2 is 1 times square root of 2, which is, we said, 1.4 about. We are approximating, so it's okay. square root of 3, which is 1.7, and then A4 is times square root of 4, which is 2. So now area is approximated by A1 plus A2 plus A3. What happened? 6.5. 6.1. 6.1. Excellent. True area exact area, whatever, is going to be between these two numbers, 4.1 and 6.1. These are terrible answers. I mean, the margin of error here, the tolerance. Try to use this tolerance to build a car, right? So, can we do better? And the answer is yes. Is it gonna cost you something? Yes. No free lunch. To make this better, you put in more rectangles. So, at the cost to have a better answer, better range, you're going to pay more calculations. When your calculators do these things, they're programmed in 10,000, 100,000 of these. I have a student in Calc 2 who loves these things, loves to program. So we did the improvement method. I told you the improvement methods are in Calc 2. So he programmed in to use 1 billion rectangles. So he coded in class to do the whatever amount, 10 or 100, whatever, which is still better than the 6 I did in class, and I was annoyed by the end of the 6 rectangle calculation. And then he went home and he improved on that code, and I believe he also said that the final product, the 2 billion, which is way too much, because it becomes a trade-off of computing power and the time it takes to the actual precision that you need. So, right now, I am going to tell you the quote exact answer for this, which is the one that you get on. Oh, this is not on? Wow. This is the one that you get with the calculations that we are going to develop. Well, apparently I won't give you that anytime soon because this thing has to boot for another 25 minutes. So, to improve on the interval, use more rectangles. I used only 4. Go ahead, use 10. And you are going to have better approximation. The more you use, the better your answer is. Is there a way to actually get the exact answer? The answer is yes. How many rectangles do you have to use? The answer is infinitely many. Which means you're gonna sit here like elves eternally, right? And for eternity, calculate this one by one. So those are the left-hand sums and right-hand sums. What can I change? I can change the number of rectangles, depending on how annoying I want to be. Your homework examples will have 4 rectangles, 8 rectangles, 16 rectangles, right? So it's much better if you code this than you can code this in Excel, for crying out loud, right? You don't have to go Java or anything. And I can change the function, right? Because I calculated the height by plugging in values of these numbers, right, into height. So when I have the picture and I have my representative rectangle, I'll call this AN. This distance over here is called the delta x because it's xn and xn minus 1. So if this is, let's say, a fourth point, then the one before that is a third point. Delta x is b minus a over n. This formula is your length. So n is the number of triangles and a and b are your interval. We had the interval 0 to 4 to calculate for our root. So n, number of rectangles, if you are going to code this, make sure you put a user input. Do not hard code 4 or 6 into the software, right? Ask a user to input the number, and you put n as a variable and then assign whatever the user tells you, assign that there. A and B is the interval on which we're calculating. So that's that. Height is equal to f of xn. So height is calculated at each point that needs to be calculated, and this is the height. So area is going to be A1 plus A2 plus A3 plus dot 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 going to whatever value you need to. And each one of these AN areas is calculated as length times height. For those of you that never dealt with computer science and you're not sure what these indexes are, this index n can only take on values 0, 1, 2, 3 integer values, because that is the counter. It simply counts from 0 to whatever. So partitioning. Interval is 1 to 7, and the number of rectangles n is something that I'm not going to, 5. I just want to make it as disgusting as possible. I'm not giving any function. I just want to do the partition for x-axis. My numbers start at 1 because that's my A. Now I'm going to use this to calculate the delta x, which is a step, right? How far you go left. So to calculate delta x, I'm going to have 7 minus 1 over 5, which is 6 over 5. Yeah, 6/5. So that cannot be reduced. So now I have 1 and 6/5. So I'm just going to because I want 5 rectangles, right? I'm just gonna go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I just want to make these lines available. That's your x-axis. So you start with A, which is number 1, and then you add 6/5 to it. So 1 is 5/5, so that's 11/5. And you just keep adding 6 now. 17/5, 23/5, 29/5, plus 6 is 35/5. Guys, what's 35 divided by 5?
7.
That should be. If this doesn't hit its target, you did something wrong. So when you start adding, my first example had these divisions at 1, 2, 3, 4, 5, right? That was easy. You can have fractions, right? Decimals, whatever. So to calculate delta x, you go b minus a over 5, and you are done. So let's take a look. This is going to be an example for you guys. I'm going to leave the partition. No, I'm going to make a new one. So excitement, because we are going to calculate area under f of x equals x squared minus 3x. I don't want to do that. X squared plus 3. That's good enough. X squared plus 3 with, let's say, 5 rectangles, so you're not sleeping here. On some, interval. How about 2 to 6? So I'm just trying to make sure you're getting fractions. So you have the problem up there. Now, I'm asking for everything. Now, how about on my left, we have the left-hand rule, and on my right, we have the right-hand rule. Sounds good? So, left-hand rule. You are all lefties. The first rectangle, left. Everyone, please look at this. First rectangle, left. First rectangle, right. Right? Because you have a left point and the right point. So all of the left points are calculated. First rectangle left, second rectangle left, right? So you guys will not be using the last point. And you guys won't be using the first point because you are rights. For the first one, that's the right. Second one, that's the right. So you end up using the last one. You don't use the first one. These guys, opposite. All right. So So partition is first. Partition goes as I start at 2, I calculate delta x on the side as 6 minus 2 divided by 5, which is 4/5, and then I start adding 4/5 along the line. So 2 is what? That's 10/5. So what's the next one over here? 14/5, and then 18/5. You keep adding 4, 22/5, plus 4, 26, no coughing, over 5, and then 30/5, which is a 6. Each one of these lengths is delta x length of 4/5. Now, for the left, I have left points. Let's do the red. AL. These are my left points, because those are for each one of these intervals has a rectangle above it, and the left points are where we calculate. So I have a function computed at 2 times delta x plus function computed at 14/5 times delta x plus function computed at 18/5 delta x plus function computed at 22/5 delta x, and finally plus function computed at 26/5 times delta x. Hopefully you see that this delta x is what you can factor out, right? And now we just compute 2 squared plus 3 plus 14/5 squared plus 3 plus 18/5 squared plus 3 plus 22/5 squared plus 3 and 26/5 squared plus 3. Left is delta x was 4/5, and now over here I have 2 squared is 4 plus 1, 2, 3, 4, 5, right? That's a 5 times 3 is 15 plus, and now 14 squared is 196 over 25 plus, and just get these and equals a number. Are you done? So we're not wasting time forever. Is it hard? No. Is it annoying? Yes. And that's the difference between hard and annoying, right? That's the difference. Now, I just want to talk a little bit more about this partitioning, because we are going to use it in our next lecture, which is the spicy one. And that is the fact that your partitioning starts from A. Now, that A sometimes is 0. Last time we had it at 2, right? Could be any number. So, could be negative. So, A is the value on x-axis where your partition is starting. And then you have the next value, and that next value is A plus delta x, because there is a delta x difference between the two. So that's how I quickly come up with all of the partition. I just keep adding delta x every time. The next partition also has delta x in between, and that's going to be A plus 2 delta x. And then the next one has delta x, another delta x, so that's going to be A plus 3 delta x. So do you see how for each one of these, you have A, and then plus some amount of delta x's. A plus 4 delta x, and I'm just going to put 3 dots. What we can do, right? So eventually, after the 3 dots, there's going to be a B, and that's the end. Now, these are my x values. This is my x0 value, x1 value, x2 value, x3 value, x4, right? Those are the whatever numbers they work out to be. So what is the formula for xn? Sorry, we use xi as a counter. Again, I is a counter. Hopefully you see that this is A plus I delta x. This is actually a formula. We are going to use this formula after the break. Calculates all locations on the number line. For partition, yes. So do you actually have to have every single partition? Maybe I am interested only in partition 7. Great. I equals 7, and you can compute as A plus 7 times delta x. And you immediately have all the way there, right? Any computer science geeks in tonight? Right? That's your stuff, right? Discrete, that's your stuff. So shifting these counters and making these equations to find location, right? In the array, sequence, right? So this is what it does. So do we see that our x2 value can be easily computed by placing a number 2 there? So A plus 2 delta x, which is exactly what it is. Now we know what delta x is, was 4/5 earlier, and A was 2, so 2 plus 2 times 4/5. You get the value like this. So you can pull any value quickly, and in addition to pulling any value quickly, you can also have all of this in this nice compressed formula, which will play the role in 5.2. So what's here in 5.1? We are taking whatever curve we have, we are breaking that, partitioning, we're breaking that into small rectangles, computing each rectangle separately, areas, and then we just add all of those areas together. After the break, 5.2, the title is Definite Integral.